Okay, so this is going to be the last video for section 3.4, and we're going to cover example 5. Now, in the past ones, we've only dealt with linear factors, right? In fact, if you looked at one of the first examples we did, example 2, we actually had a quadratic factor, the x squared minus 3x plus 2, but we were able to reduce it to a linear factor, and you're always going to want to do that whenever you can. But in example 5, we have a quadratic factor that is not reducible. So right here, this is a quadratic factor that is not reducible. And so when we go ahead and decompose it, things are going to look a little bit different. So let's talk about that. We have 3 over a linear factor x minus 1 times that irreducible quadratic factor. And so the linear factor, of course, we know from the previous examples, looks like a over x minus 1. But the quadratic factor, since it's x squared plus 2 in the denominator, the top is going to be linear, so bx plus c. And we just keep moving on to new variables here. So when we have a quadratic denominator, the numerator is going to be linear. And so let's go ahead and come up with our identity. Let's multiply both sides by the least common denominator, which when we do that, we get 3 is equal to a times x squared plus 2 plus b times x minus 1. Actually, excuse me, not b. What should that be? bx plus c times x minus 1. Okay, so now we can go ahead and try to figure out what a, b, and c are, like we have in all the past videos. I'm going to go ahead and start with x equals 1. I think that's probably the easiest. And so when we plug in 1, we get 3 equals twice a plus 0. So a, actually, I'm sorry, that's not 2a. What should that be? 1 squared plus 2 is actually 3a. My fault there. So we have 3a, and then when we plug 1 on the second part, 1 minus 1 is 0, so that goes away. So this tells us that a equals 1. That's the easiest one to find, but it's not going to be too hard to find the other ones. I would go ahead and pick 0 next. There's no obvious one, but 0 is an easy one to plug in. And since that will give us some, let's just pick our next biggest positive number. Let's go x equals 2. So we'll do those 2 problems. So first of all, when we plug in 0, we get 3 equals 2a plus b times 0 is 0, so plus c times negative 1. And we know a is 1, so this is 3 equals 2 minus c, which means c is equal to negative 1. C equals negative 1. All right, so, and then the last one, when we plug in 2, we get 3 equals 2 squared is 4 plus 2, 6a plus 2b plus c times 1. But of course c is negative 1, so we have 3 equals 6a plus 2b minus 1. We also didn't plug what a was equal to. A was equal to 1, so really that's just equal to 6, right? So that's 6 times 1, or 6. And 6 minus 1 is 5, so we subtract 5 to the other side. We get negative 2 is equal to 2b, which means b is equal to negative 1. And so now we can go ahead and rewrite our integral. Our original integral can be rewritten. It can be rewritten as the integral of 1 over x minus 1 plus, well, that's b and c are both negative 1. So rather than writing it with a plus, I'm going to write this as a minus, and then you basically have x plus 1 over x squared plus 2. And the first one is easy, right? The first one, the integral of 1 over x minus 1, that's just natural log. But we can go ahead and rewrite all of these really into 3 separate integrals. So I would say this is equal to 1 over x minus 1 dx minus x over x squared plus 2 dx minus 1 over x squared plus 2. So basically what we did is we just split this fraction. Instead of x plus 1 over x squared plus 2, it's x over x squared plus 2. That's the first integral, plus or minus, because that minus gets distributed, minus 1 over x squared plus 2. And the reason why we want to split up this last fraction, the x plus 1 over x squared plus 2, is because that is an integral that we just don't know how to deal with. But if we split it up, we can definitely deal with these 2 remaining ones. Now, the last integral, the 1 over x squared plus 2, we're going to use this fact that I just boxed up there as part of your notes. We're going to use that to evaluate the second one. But what method are we going to use for the middle integral? You think about that for a second. What method would we use there? All right, well, hopefully you chose that we would want to use a u substitution. So we want to let u equal the denominator, because that's a quadratic, and when you take its derivative, you get 2x, which is like our x that we have up there. So that's going to work nicely for u substitution. That tells us that dx is equal to du over 2x. And so that second integral can be rewritten as the integral of x over, we have u times du over 2x, and the x's cancel. We also know that the first one, that's a simple one, that's the natural log of x minus 1. And then the last one, like I said, we're going to use the fact that the integral of x squared plus a squared is 1 over a times the inverse tangent of x over a. And what would a be in this case? So notice it's not quite the same. This integral looks like x squared plus a squared, and our integral is x squared plus 2. So what would a have to be equal to? Hopefully you chose that a should be the square root of 2, and that's because when you plug, if you were to plug root 2 in for a here, we would get 2 like in our problem. So we just follow the formula. So this is going to be minus 1 over root 2 times the inverse tangent of x over root 2 plus c. And we're almost done. This is the natural log of the absolute value of x minus 1 minus the natural log, well, don't forget our 1/2. We have that factor of 1/2 there. So we have from the 2x, right? The x is canceled, but we still have the 1 over 2 times the natural log of the absolute value of u minus 1 over root 2 times the inverse tangent of x over root 2 plus c. Then we have to back substitute for u. So our final answer is the natural log, absolute value x minus 1 minus 1/2, the natural log of the absolute value of x squared plus 2 minus 1 over root 2 times the inverse tangent of x over root 2 plus c. And that's as far as we can go for that example. Now there is one more example in this section, and that's example 6. And this one doesn't actually ask us to evaluate, but it does ask us to go ahead and decompose the partial fraction. So think about all the different factors we have there, which ones are linear, which ones are quadratic, and go ahead and write on your own, pause the video, write on your own, what do you think that would work out to? Okay, so you should get, let's start with the x cubed. So that's a linear factor, but it is cubed, which means we're going to have 3 separate terms for that, right? We're going to have a over x plus b over x squared plus c over x cubed. And that's because it's a linear factor cubed. So we have to deal with the x squared, and the x cubed. The next one is a linear factor, x plus 1. So we have d on the top. That's constant over x plus 1. What about the next one? Our denominator is x squared plus x plus 4. That's an irreducible quadratic factor, which means we're going to have a linear expression on the top, which is going to be ex plus f. We're just moving along through the alphabet. And then we also have another irreducible quadratic factor in x squared plus 3, but that is squared, so that requires 2 more terms. We have x squared plus 3, but then we also have x squared plus 3 squared. This is much like the x cubed that we dealt with at the beginning. So the top of this one is going to be linear, gx plus h, and then the same goes for the last one, ix plus j. And we don't want to try to evaluate this or find out what all those constants are. This was more just practicing how we go ahead and decompose. So that's going to do it for section 3.4. Thank you for your time.